let's get into the talk. Today's talk is hacking and securing iOS applications. So basically, iOS is an Apple-designed operating system which comes with a lot of security features. But all of them security features are subject to attack. So if an application security is completely depends on iOS, the application security can be broken. So today's presentations, I will be covering overview on iOS security concepts and loopholes in iOS, and how does these loopholes affect iOS applications, and how an attacker can steal data from your own applications, and how to protect these applications. So by the way, how many are mobile app developers here? Nobody? Okay. Okay, there are few. Fine. So a slide about me. I worked as a developer for 1 year and I moved into security. It's been 5 years in security. I've been working on web applications and mobile applications. And my personal interests are iOS forensics and iOS hacking. I've developed a couple of tools for hacking community. So we'll start with the basics. iOS operating system is it's an operating system developed by Apple and used in all of the Apple devices like iPhone and iPad, Apple TV, iPod, which is a stripped down Mac OS X, which uses Xeno kernel and which comes with a lot of security features compared to Mac OS X, and which provides multitasking, and Apple adds a lot of security features and fixes many bugs with every release. And the current release up to is iOS 6.0.1. The techniques which I am going to cover today works with 6.0.1. So iOS security starts from its booting process. Like when we switch on iPhone, a series of signature checks happens among different OS components. Like when we booted the iPhone, first boot RAM gets loaded, and then the boot RAM verifies the signature of low-level bootloader, and it verifies the signature of second bootloader, and the bootloader verifies the signature of kernel, and the kernel verifies the signature of file system. The signature check makes sure that the OS is not modified by anyone. And thereafter, the code signing mechanism implemented in the kernel basically prevents running of unauthorized apps on the file system, which is basically designed to prevent the malware on iOS devices. That is the reason we see less malware compared to Android devices on iOS devices. So like for layman, code signing and boot chain really doesn't matter. So what they need is they want to set a passcode for the device, and if they set a passcode, nobody should be able to access the data. So iOS also provides a passcode option like which prevents unauthorized access to the device, and by default it's a 4-digit passcode, and it also supports complex passcode, and we can also configure data wipe after certain failed attempts. So like fine, is there any possibility to access data without supplying a passcode? Suppose I'm a user, I found a phone, someone else's phone, which is passcode protected. So is there any way to access the data without passcode? There is a way. Suppose let's take an example of a laptop. So laptop, we have a hard disk, and suppose if I want to assume that it's a Windows laptop which is passcode protected. So there are a couple of ways to grab the data from hard disk without knowing the passcode. One is we can take the hard disk out of the computer and connect it to some other computer. Another one is boot with live CD and access the file system. The same thing can be applied to iPhone as well. So, but it's easy to remove the hard disk on laptop, but it is difficult to remove the flash memory chip from iPhone. So there are a couple of ways to read the data without supplying passcode. One is take out the flash memory chip and connect it to another iPhone or a chip reader. Another one is load your live CD onto the iPhone. So one way, because of series of signature checks, we cannot load our custom OS onto the iPhone. So in order to load our custom OS, first we have to identify a vulnerability in boot RAM and then exploit it. Later we'll load our custom OS onto the iPhone over USB cable. So once we load our custom OS, we can pretty much access the file system as we did in a laptop with live CD. So these boot RAM exploits are available since iPhone 4, and which are already identified in iPhone 4 and iPhone previous. And the hackers are still working hard to find out these kind of boot RAM exploits in 4S and the latest devices. Fine. So how does Apple prevent those kind of attacks? So it is very clear that people can access data without supplying the passcode. So Apple come up with encryption kind of thing. In the case of laptops, we can protect the hard disk with full disk encryption software. Like in those cases, the hard disk content is encrypted. So even if you take out the hard disk and connect it to some other machine, it is encrypted, we cannot read it. The same concept was implemented in iPhone as well. So iPhone comes with a separate crypto engine just for performing the encryption and decryption. The crypto engine basically comes with two hard-coded keys, UID and GID. UID is unique for device and GID is unique for the model. So UID is like for every is used to encrypt the file system on the iPhone, and when you are updating, the OS itself is encrypted. So Apple designed the OS with encryption because nobody can easily reverse it and find vulnerabilities. So when we are trying to update our iPhone, the complete OS is encrypted, and the GID on the iPhone will decrypt the OS and loads it. And also, Apple came up with the data protection in iOS 4, which basically ties the encryption to the user's passcode. Like previously, when a user sets a passcode, it just protects the screen, but it does not protect anything on the device. So with data protection, if a file is marked as protected, then the passcode can be used to encrypt the file. And even if there is if the file is marked as data protected, if the user does not set a passcode, and there is no data protection, because file is encrypted with the user's passcode, and user did not supply any passcode, so it's not encrypted. And look at the file encryption. There are different stages in file encryption. So on an iPhone device, every file is encrypted with a file key, and the file key is stored in the metadata. And the file metadata is again encrypted with file system key, which is generated from the device UID. And if the file is marked as protected, it is also encrypted with a class key, which is generated from the UID and the passcode. This much complicated files are stored on iOS device. So this is fine, and the data is tied encrypted with the user's passcode. Is there any way to bypass the user's passcode? Yes, there are ways. Like once we do it with a custom RAM disk, we can access the file system. And the good thing about iPhone is passcode is not stored anywhere on the device in any format. They are not even stored in hash format. So there is only one option, brute force. So we can do it at two levels. On the Springboard level, like from the UI, if you do a brute force, after 6 attempts, it starts introducing a delay. And the delay goes from 1 minute to several hours. So you can see the image, which basically says there are a couple of days are required to brute force the passcode. And brute forcing at a kernel level, like once we booted with the custom RAM disk, the passcode is basically valid. Passcode validity is verified by locking and unlocking a system key bag. So when a user supplies a passcode, iPhone generates another key from the passcode, and the key is used to encrypt the system key bag. So if the user supplies a valid passcode, then only the system key bag gets unlocked. So we can load our brute force script at the kernel level using a custom RAM disk or a custom OS, which we can load it using through USB cable, and later we can perform a brute force attack, and we can grab the passcode. So these are the time required to brute force a passcode of an iOS device. Suppose we take an example of iPhone 4, it will take 18 minutes to brute force the 4-digit passcode. So along with those concepts, iOS comes with a lot many security features like address space layout randomization, which basically randomizes the memory address of every application, and data execution prevention, and stack canaries, which basically protects buffer overflows. So if someone wants to find a jailbreak vulnerability, they have to bypass all these security measures. That is the reason jailbreak has a lot of value in the market. So if coming to the iOS software stack, like all the security features which we have discussed comes under core OS layer, and the core services layer provides APIs to use the services, the security features which are in the core OS layer. So if someone is building an iOS application, they will use the first 3 layers like application, Cocoa Touch, and media layers, and use the security APIs provided by the iOS and build their application. So like there are 3 types of iOS applications available. One is browser-based, which is completely web-based application which runs on the Safari. Another one is native application, which is built with iOS SDK and compiled for iPhone CPU, and which are basically written in Objective-C. And hybrid applications, which are basically like a native container that leverages the both native and the browser based applications. We can take an example of Facebook here. Facebook designed their native GUI, and from there on, they use HTML5 to load the content. It basically uses both native and the browser based. Coming to our favorite thing, areas of hacking. So coming to the iOS applications, there are mainly three categories for the areas to focus. One is device storage, where if I found an iPhone of someone else, how much data I can steal, what data I can steal. So then think runtime analysis and network scripting. We'll be looking at each and every part in detail. Coming to the local storage. So iOS application installed on iPhone. So every iOS application gets us these directories. So if you install an iPhone application on the iPhone, on the background it comes with all these directories. And the iOS application runs in a sandbox environment where it does not have access to another application. And iPhone has two users, one is root and another one is mobile. And the mobile, all the applications runs with mobile user who has lesser privileges. So iOS application can store the data in any format. So coming to the different areas of storage, property list. The developers prefer property list because it is easy to use, or it is easy to develop using property list. It's basically a key value pair stored in a binary format, or it could be in XML format. Most of the developers prefer the binary format because of space constraints, and the binary formatted property list can be used using property list editors. So Apple designed this property list basically to store the configuration information. Like suppose if you are playing a game, the property list can be used to store the score or the level which you are, such kind of configuration information. So, but what happened is it is easy to use. So application developers started storing usernames, passwords, and session-related information in the plist file. So this is an example of Facebook plist, which they store the session information on the plist. And the plists are also not protected by data protection, which means it is not encrypted with the user supply passcode. So I wrote a code called FileDP, which basically fetches the file attributes and displays whether it is protected with the passcode or not. And also, like when we using iTunes, we can take a backup of iPhone. So once we take an iPhone backup, the plist files also get stored unencrypted on iOS backup. It's basically like we are moving the files from the iPhone to the computer. So if someone exploits our computer using any other vulnerability, they can get access to our backup, which means they can also steal our phone data. And there are applications which delete the plist files upon logout. You can take an example of, suppose there is a bank application where it is storing the username and password in the plist file. So after login, it stores the username and password, and after logout, it deletes the plist file. So, but iOS file system records the changes in a HFS journal. HFS is the format used in the file system. So we can use forensic techniques and recover the deleted files as well. So we'll take a look at the real world scenario. So of Facebook session hijacking. So Facebook stores authentication token in a plist file. And if you gain access to the plist file, we can log in as Facebook user. Suppose I found someone else's iPhone. So using custom RAM disk, I can grab the plist file and load the plist file in my phone. Then I can log in as their account. So the plist files can be stolen in two ways, mainly upon physical access to the device, or if the user takes a backup using iTunes, then we can exploit the system using some Metasploit and then grab the files, iOS files. So I wrote a Metasploit post-exploitation module, which basically reads the iOS backups from a device, from a computer. In addition to that, Facebook never exploit the tokens even after logout. So they store the tokens in a plist file, and even if I click a logout, it just deletes the plist file, but it never exploits the tokens. So if I get a plist file which is a long time ago, I can still log in as that user. So I reported the problem to Facebook and they fixed it. And the problem is fixed a couple of days ago. So moral is like do not store any information in the plist file because they are not safe, and people can easily grab the plist file. So if required, use custom encryption while storing the information in plist file. Also use data protection, basically ties the encryption to the user's passcode. And also create plist files in library caches folder in the application directory. So iTunes does not take a backup of files which are stored in the caches folder. Also, for better security, if you are deleting any files upon logout, so just override the file before deleting it. So even if forensic techniques can be used to recover the file, the content will be janked. So these are the different data protections for files. Like you can use NX protection complete, which basically the file is inaccessible until device is unlocked, or you can, these are different constants, data protection constants that can be assigned to a property list, key list file. So now coming to the Sqlite files, there are lightweight database and structured data storage. So they are portable and easy to use single fact files. So Sqlite is preferred by many developers because memory usage and speed is better compared to key list files. So there are applications used to store plain text usernames and passwords and many things in the Sqlite files as well. So this is a screenshot of the Gmail application. They store all the messages in a Sqlite file and in plain text. So again, the data stored in the Sqlite is unencrypted, and it is again copied to iTunes backup in an unencrypted fashion. Apps may delete the Sqlite files, which we can grab by carving the HFS journal. There are apps which basically delete the Sqlite records. Let's take an example of, we'll take a demo. So I wrote an application called card info, which basically takes a username and password, and which acts like a passbook where the user stores the username and credit card information in the application. So on the right side, I used that's my phone. I used the VNC client on my system and VNC server on the iPhone, and displayed the iPhone on the screen. So using SSH, I browsed the application and looking at the card database Sqlite 3, that is a Sqlite file, which is used by my application. So now I am opening the application and entering username and password. So once I enter the username and password, it basically prompts the user to enter the credit card details for saving purpose. So the user is entering his credit card details. Once he entered the credit card details and clicked on save, the information is stored in the Sqlite file, and we can use a fetch command, select star from card info, which basically fetches the information from Sqlite file. So I clicked on logout and it deleted the content from the Sqlite file. It seems every secure because after logout it is deleting the file. But when I use the strings command, we can still fetch the deleted data from the Sqlite file, which means I can still grab the credit card information and CVV number from Sqlite database, even if the application has deleted it. So even if application deletes the data from the iPhone, using forensic techniques, we can still recover the data. So more or less, do not store any sensitive data in clear text on Sqlite files. Use always custom encryption and protect the Sqlite files with data protection. And also implement classes for secure file wipe. And if you are deleting a record from a Sqlite, override the content so that even if forensic techniques are used, the junk data will be recovered and the original data will be safe. And there is a command on Sqlite which is basically vacuum, which rebuilds the database and removes the uncommitted data from the Sqlite. So if you are building an application, use this command. And another place is keychain. Again, Apple says keychain is a secure place to store the username and password. And it is located in keychains folder on the iPhone. It basically contains 4 tables. One is generic password, internet passwords, and certificates and keys. Keychain encryption is tied to the device, so even if the keychain is moved to some other place, it cannot be decrypted because its encryption is tied to the device. And we can also mark the keychain entries with the data protection. So keychain is basically accessible to all the applications, but items in the keychain are accessible by its own application. So suppose if application A is added a content to the keychain, it can only access that particular entry. It does not have access to any other entry. So on a jailbroken device, these restrictions can be easily bypassed, and it can be bypassed like we can design an application which is a member of all the keychain groups, and once we run the application, it basically fetches all the entries from the keychain. And there are a couple of tools available in the market. One is keychain dumper and keychain viewer. We'll take a look at the keychain viewer. How does it look? So this is the keychain viewer demo. So I'm basically using an SSH. I'm browsing the folders which are in the iPhone. So I move to the, I open the keychain database and use the select command. And now you can see the data, all the data is encrypted on the keychain DB. So I've downloaded a keychain viewer application, and looking at the generic passwords, it fetches all the passwords from the keychain and listing in the application. So Belkin 3239 is my access point, and that is the password of my access point. So basically, data stored in the keychain is not secure anymore. So use custom encryptions if you decided to store something in the keychain, and also use data protection keys. These are the different data protections that can be used in flagged for the keychain entry. Error logs, and for debugging purposes and troubleshooting, applications do write sensitive data in the logs. So if you are, and all the logs are located in the syslog folder, and the logs can be easily viewed. And syslog is out of Sandbox, which means like any application can access your log report. So during assessments, I found many applications are logging data, like logging requests and responses and credit card information. So we'll take a look at the example. So here is an application, the same application which I have shown previously, the card info. So I'm entering the username and password. So once I enter it, again asks for the credit card details. I'm filling the details. So once I fill the details, I've used the iPhone configuration which and connected the iPhone over USB. Now you can see the application has logged the credit card number and all the things in the syslog. And the syslogs can be easily viewed using iPhone configuration utility, or it can be used. You can see using a console application downloaded from App Store. Screenshots, like when we press a home button on iPhone, the application gets synced with a nice effect. But in order to provide that effect, iPhone takes a screenshot of your application, and the snapshots are stored in the caches folder. Suppose this is an application when I'm browsing a Citibank statement on my iPhone Gmail application, and I press the home button, and the Gmail the iPhone took a snapshot of that statement. So in order to avoid these kind of screenshots while developing, remove sensitive data or change the screens to blank before transmitting the application to the backside, or remove the background running option. So while designing the application, this is a keyboard cache where iPhone records everything that a user types on keyboard, and all that is basically to provide autocomplete feature, and all the data type gets stored in the DAT file, which can be used using hex editors. So if you are designing an application, and by default the passwords are safe, autocomplete is disabled for password fields, and autocomplete is also disabled for PIN and credit card, such kind of information. But so username and security questions are still vulnerable. So if you are designing an application, disable the autocomplete of particular field by making it as a secure field, or disabling the auto correction. And the cookies.binary cookies, like many iOS applications, basically does not want to prompt the user for every time for login. So they create persistent cookies and stores on the device. And the cookies are stored in binary format, which is basically cookies.binary cookies. So if we grab that cookies binary, we can log into that user account. I wrote a Python program which is binary cookie reader, which basically takes in cookies.binary cookie file and displays the cookies. So for critical information, do not create persistent cookies. So let's get into the runtime analysis. Like App Store binaries are encrypted because to protect from piracy, all the files which we download from the App Store are encrypted. So first, in order to perform a runtime analysis or looking at the binary, first we need to understand it. So we need to decrypt, and we do not have the key. So what we will do is we load the application onto the iPhone. We'll instruct the iPhone loader to decrypt the application for us, and it loads into the memory decrypted. And we'll use some GNU debugger or some debugging tools and fetch the decrypted app from the memory and put it into file, and we'll reconstruct the decrypted application. So instead of doing that, we have tools like Trapless and Installers, which basically decrypts the apps which we downloaded from App Store. Once we download the application, use GNU Debugger or IDEA Pro and analyze the binary to find out whether it is storing any encryption keys, hard-coded passwords. And to do runtime analysis, we can use another tool called class_dump, which basically, when we run it on a decrypted binary, it lists out all the classes and methods of a particular binary application. So once we identified all the classes, we can analyze the dump to identify the interesting classes. So later we can use a Sqlite, and the Sqlite is basically like JavaScript and Objective-C interpreter, and which can be directly hooked into an application. And once we hook, we can access all the objects inside it, or we can actually modify the objects, functions, or instance variables. Let's take a look at the demo. Yes. Basically, the video I've developed an application which basically takes an username and password, and once we log in, it shows a welcome screen. It doesn't do anything. It could be your bank application or any mail application. So I'm using an SSH and connected to the device, and by the way, the device is already jailbroken, so I can do an SSH. Once I did an SSH, I go into the application name, and on the application, I'm performing a class dump, which basically dumps all the classes and methods, instance variables from the binary. So once I look at the classes, I analyzed it and identified a couple of interesting classes. So by analyzing the classes, I'm using a Sqlite to hook that process. First, I identified the process number using psax command. Then I use the Sqlite to hook the binary. Once I hook the binary, every iOS application starts with UI app object. So I've taken that UI app object from the Sqlite. So now you can see the runtime interactions. Now I'm changing the key window from login window to a home screen. So once I change this, once I enter this command, it automatically logged into the application without applying any username and password. So with Sqlite, we can hook into the applications and modify the behavior of the applications at runtime. So the possible attacks which can be performed using Sqlite is like authentication bypass and breaking simple logs. And there are applications which built to so they are built in such a way that it does not run on jailbroken devices. So we can modify those applications as well. Also, we can extract hard-coded encryption keys and passwords. We can also add our own code. So the moral is do not store encryption keys or passwords in memory, and implement code that restricts the debugger attachment. And coming to the last part, this is the transport security. Like iOS applications use HTTPS to do secure transport transactions. And there are a couple of classes which are used to implement the SSL, but all of them are designed in a secure way that they won't accept the self-signed certificates, but they provide APIs which will make them to accept untrusted certificates. So you can see the poster right there. Don't ignore them. So similarly, you can see the same kind of error messages on iPhone as well. So if you are developing an application, do not write a code such that it accepts the untrusted certificates. And APIs by default supports a lot of weak ciphers. So if you compile the application using the latest SDK, it doesn't support any weak ciphers.